Okay, shall we begin? I'm Tim Adamo, obviously not Sabrina Pisterski or Anna Reclari, but I'll do my best impersonation of them. But let me give some kind of parental advisory before these lectures start. So celestial holography means many things to many different people, and it's not at all clear that what it means to me is what it will mean to some of you in the audience already, so I'll apologize in advance if I don't tell you things you were hoping to hear or tell you things you were hoping not to hear. But I'll try at the beginning of each lecture to kind of give some reference reading so that you don't just have to take my word for it. You can go for yourself and convince yourself whether I've been lying to you or not. Okay, so the starting point for us today, and I think it's fair to say one of the starting points for this whole field, is the following extremely simple observation. When we're in our first quantum field theory class, most of us learn how to compute scattering amplitudes. And the way we do this, or the way we're often taught to do this, is via this thing called the LSZ reduction formula. So what does this mean in words? It says you have your favorite quantum field theory, you're trying to compute scattering amplitude in it. It says you take a correlation function of local operators, you drag these local operators off to infinity in such a way that some of them become part of an in state and the others become part of some out state, and then you put them all on shell. And what that means is that the external states in the scattering amplitude in the S matrix, these things are solutions to free equations of motion. So in most textbooks, when we learn about the LSZ reduction formula, there's some kind of more or less complicated statement involving extracting poles of this correlation function after you've Fourier transformed it. But actually, you'll note that none of the words I just said made any reference to that. And I think this is an important fact that we often lose sight of when we learn about quantum field theory for the first time, is that although it's often formulated in momentum space, the kind of impetus of this LSZ prescription doesn't have anything to do with momentum space. It's just telling you how to go from an off-shell object in a quantum field theory, which is a correlation function, to some on-shell object that's an S matrix element. Okay? So typically, we represent these external states in a momentum basis, so as momentum eigenstates. Right, so suppose we were considering, I don't know, your favorite scalar quantum field theory, maybe phi to the fourth. So, for instance, scalar momentum eigenstates, these are things that just look like e to the minus or plus I p dot x, where this minus plus corresponds to whether the state is incoming or outgoing. Right? And then this momentum p obeys some mass shell condition, and that is the equation of motion that LSZ is imposing, right? So to define your scattering amplitude. So for today, we're going to assume that we're computing scattering amplitudes in four-dimensional Minkowski space until further notice, and we're also going to assume that our external states are massless. Now, if massless scattering gives you the howling fantods because you've heard of things like IR divergences, don't worry. In the back of your mind, assume that we're doing everything perturbatively and assume that we're doing it at tree level. So none of this stuff is going to bother us, okay? It might bother us if we decide to be more sophisticated, which maybe we will be in later lectures. Okay, so what this means is that in a momentum eigenstate like that, PA is null, so a null 4-vector. Here I'll use lowercase Roman indices for space-time indices. And we also typically make an assumption, say that the energy associated or frequency associated with the states is positive. Okay? Now, from a mathematical perspective, this is a well-defined assumption because, of course, the things we actually scatter in an experiment are not momentum eigenstates, right? Wave packets. So what we're really doing when we compute an scattering amplitude with these things as the external states is we're saying, well, we compute this scattering amplitude for these momentum eigenstates and we're going to convolve it with wave packets to give us something that actually looks like what we might cook up at our collider. But for that to make sense, we want to believe that things like this form a complete normalizable basis of the space of all the solutions of the linearized equations of motion, right? And that's only true if this P naught is greater than 0. Okay. So there's kind of a physical reason, but also a mathematical reason for this restriction. Okay, but, okay, so this, I said that these assumptions imply this, but of course, those assumptions are dimension agnostic, and the first thing I'd like to do is talk a little bit about what it means to have a null vector in 4 dimensions, and why that's kind of a more fun game to play than in a generic number of dimensions. So let's talk about parametrizing null momenta in 4D. Okay. So let's let sigma alpha alpha dot A be our Pauli matrices. Now, of course, this involves some choice of convention. I'll shortly fix what my choice of convention is. Any choice will work. And then if I'm given a 4-vector, PA, I can use these Pauli matrices to form a 2x2 to uniquely associate a 2x2 matrix to that 4-vector. I'll call that matrix P alpha alpha dot, and that's just given by taking my 4-vector PA and contracting it into the 4 Pauli matrices. Okay, so this gives me some 2x2 matrix. And again, my conventions for this will be the following. Okay, so this is a very practical just algorithm. I hand you a 4-vector, you crank out this 2x2 matrix. A more mathematically sophisticated way of saying this is that there's some local isomorphism between the complexified spin group in 4 dimensions and 2 copies of SL2. If those words illuminate the situation for you, so much the better, but it doesn't really matter, right? This is just some prescription. I can uniquely associate a 2x2 matrix, P alpha alpha dot, to every P, 4-vector P. But now, if you look at this 2x2, partition that off for us here. So if we look at this 2x2 matrix, you don't have to stare at it too long before you see it has some nifty properties. So you can observe that the determinant of this 2x2 matrix is precisely a half times the Minkowski norm of the 4 vector we started with. So, okay, you might say, well, all right, that's an interesting observation. What does it buy me? Well, it buys us something interesting precisely when this 4 vector is null. So like a momentum for a massless particle. So it's the case that the 4 vector is null if and only if the determinant of its corresponding 2 by 2 matrix vanishes, right? And we know lots about 2 by 2 matrices with vanishing determinant. Either they're rank 0, which means they're not interesting, or they have to be rank 1, which means they have to be simple, right? So this is the same as saying that P alpha alpha dot can be written as a product of 2, if you like, 2-dimensional vectors. Often we call these things spinners because these alpha alpha dot indices are really properly thought of as Weil spinner indices for the 1/2 0 and 0 1/2 representations of SL2 cross SL2. Again, you can let that go in one ear and out the other if you want. But yeah, so what this means is that usually the null condition is like a quadratic condition on the components of a 4 momentum, right? So usually p squared, this is p0 squared minus, so I goes from 1 to 3, pi squared equals 0. And if I say, give me the data of a null momentum, you have to solve this quadratic condition. But the advantage of working in this SL2 spinner framework, if you like, is that it gives an unconstrained way to parameterize null momentum, right? So what this is saying is that every null vector can be written as a product of these SL2 spinners, and every product of SL2 spinners is a null vector, right? So now if I say, give me a null vector in Minkowski space, you just have to give me two component Weil spinners and you've solved the problem. There's no solving a quadratic constraint or anything. So to make it more obvious, this fact that the determinant of the 2 by 2 matrix is proportional to the norm of the 4 vector means that we can replace eta AB, the Minkowski metric tensor, with some SL2 invariant objects. And the natural thing to replace it with is just the natural SL2 invariant tensor, which is the Levi-Civita symbol in 2 dimensions. So my conventions for this will be that epsilon alpha beta, this is just the 2 by 2 matrix 0, 1, minus 1, 0, and it's the same for the dotted representation. Okay? And you can easily convince yourself, fun exercise, take this 2 by 2 matrix and compute its norm with respect to these guys and make sure that you get p squared. You will. Okay, so working with this kind of SL2, so okay, there's some code terminology that I'll use again and again. So this way of replacing four vector indices with pairs of SL2 indices this is something I'll often refer to as the two-spinner formalism. So if you hear me or anyone else bandy this word around, this is all it means. It just means it's something algorithmic. Take your favorite tensor, form, expression, vector field, whatever, and replace all of the kind of vector, or tangent, or cotangent bundle indices with pairs of alpha and alpha dot using this algorithm. You just contract with the Pauli matrices. Okay. This is what we call the two-spinner. The two-spinner formalism. We've already seen one cute application of this, which is give some unconstrained way of parameterizing null momenta in 4D. Now, I was very cavalier here. I said, you give me any two of these things, and you'll get a null momentum, and that is true. But I've swept something under the rug here, which is that I've written these things like they're completely independent. And of course, they're not for Lorentzian real 4 vectors. So let me have a quick aside here. So for a Lorentzian real 4 vector, that means a 4 vector whose components P0, P1, P2, P3 are all real numbers. If this thing is null, you're not going to get independent 2 spinors. This kappa twiddle alpha dot is always going to be the complex conjugate of kappa alpha. Okay? So this is a reality condition that gets imposed on the 2 spinors. I'm not going to worry about it so much for now because it doesn't matter. You can have complex null momentum. The condition, yes, please. At the level of things I've told you so far, absolutely nothing. At the level of things I'm going to tell you in the future, much. But I'll try to be obvious about this when it happens. But let me maybe just to intervene, because it's a good question. One thing that you can gain, so I made this sermon earlier about how we're going to be thinking about doing scattering, computing scattering amplitudes. We'll be thinking about doing this at tree level, for instance. So if you have local quantum field theory, those tree level scattering amplitudes are going to be rational functions of the momenta, which means their analytic continuation is completely trivial. So continuing these things thought of as functions of some kinematic variables to complex momenta is not going to cause any problems at tree level for local quantum field theories. So it's a generalization that isn't going to hurt you at that level. Of course, it can hurt you in other ways, and like I say, I'll try to be clear about that. Other questions at this point? Okay, cool. Good, good, good. All right, so, okay, so I've given you this sermon about how you can write any null vector as a pair of 2 spinors, but in fact, this is still a redundant parameterization. That's not how you spell redundant. So why is it redundant? Because for any R, okay, so I'll use this notation often. For all R in C star, that's fancy compact way of saying all non-vanishing complex numbers are, right? So okay, for all R in C star, I can take kappa alpha, and I can send it to R times kappa alpha, and then I can take kappa twiddle alpha dot, and I can send it to 1 over R times kappa twiddle alpha dot, and I don't change the 2 by 2 matrix, P alpha alpha dot. Okay? So this C star action stabilizes, fixes the null vector. So it's some redundancy of the 2 spinor parameterization. And this has a name that we all probably know. It's the little group. Right? So the little group in physics is the thing that stabilizes a momentum vector. The little group for massless momenta in 4 dimensions is U1. So the complexification of it is C star, the non-vanishing complex numbers. And that's exactly what we're seeing here. So often, it'll be useful to kind of parameterize our spinors in a way that makes this redundancy kind of more manifest and gives a more geometrical flavor to the 2-spinor formalism. Okay, so you can, so this, just to reiterate what I just said, this is the little group freedom of massless 4 momenta. And it can be helpful to refine this two-spinner parameterization a little bit to kind of expose this. You can do this by writing kappa alpha as some square root of some energy scale, which I'll call omega, times z alpha, and then kappa twiddle alpha dot, square root of some energy scale, z bar, alpha dot, where now the scalings of z alpha dot and z bar alpha dot are going to be completely disentangled. So I can send z alpha dot to r, z alpha dot, and I can send z bar alpha dot to s, z bar alpha dot, with omega scaling to compensate. So R inverse, S inverse, omega. Okay. So you might say, well, why the heck bother with doing that? Doesn't look like I've actually bought myself anything here. But I think the nice thing that's happened here is now our null momentum is parameterized by a scale, which we're calling omega, and this equivalence class of two-component spinners. Okay, so I've cheated here notationally in an effort to make my notation line up more with the reading I suggested at the beginning. I'm calling this Z bar, but you don't need to think of it as the complex conjugate of Z, the same way that you don't need to think of kappa twiddle as the complex conjugate of kappa, but for Lorentzian real momenta, they will be. So here by square bracket Z alpha and square bracket Z bar alpha dot, I just mean this two-component object considered up to this overall rescaling, and this two-component object considered up to this overall rescaling. Right, now, some of you may already know or already met rescalings like this. This is just projective rescaling. Yes? Please.
Yes, so actually the little group, the terminology makes me confused. So because when I remind the little group in the contractive, it is a part of the isometry.
Mm-hmm.
But in this case, this little group doesn't look like any some part of this your project for C, right? So why is
this little group, the isometry interpretation of the little group is that if you had, say, a scalar scattering amplitude, it's some function of all these null momenta, and it has to be invariant under the scaling of the little group. If you had a scattering amplitude of spinning particles, it would have some prescribed scaling under the action of the little group on each of the external momenta. And that's all that's happening here. So the little group preserves the momentum, but if you have helicity or spin in the game, a kind of gauge invariant object you would build out of those momenta would have some prescribed scaling. So it is exactly the same, but formulated in perhaps these weird variables. Hopefully, at some point, I'll write down some formula for something like an amplitude, and we'll be able to see how it scales with little group. Good question. Other questions? Going once, going twice. Okay, so here, this equivalence class of two-component spinners considered up to an overall rescaling, this just defines what we would call homogeneous coordinates on the one-dimensional complex projective space, CP1. Right? So what is CP1? This is the space of, if you like, all of the lines through the origin in C2, but in very practical terms, you can describe it with pairs of complex numbers considered up to overall rescalings by any non-vanishing complex number. Right? So what we've seen is that a null momentum in 4 dimensions is parameterized by an energy scale and 2 of these homogeneous coordinates, z and z bar. Right? Now CP1, this is just the Riemann sphere, the 2 sphere. So this parameterization gives a null form momentum in terms of a scale omega and a point ZZ bar on the 2 sphere. Right? So this is something we say all the time, right? Like a null momentum, I pick a direction on the celestial sphere and then a scale. Right? And this parameterization is just making that super duper explicit. Okay? The celestial sphere is emerging in this kind of projective framework, but if you like stereographic coordinates, it's not a problem. So what you can do, if you say to me, well, Tim, you tell me that this is the sphere, but it doesn't look a lot like the sphere to me, so how do I get back to where I feel safe? So that's pretty easy. And also, let me give another caveat here. I said Z and Z bar give some point on S2. That's only true if Z bar really is the complex conjugate of Z. If it isn't, then what it gives you is a point, one copy of S2 identifies the diagonal in that Cartesian product. But it's not so important. So how to see how do we see that CP1 thought of as the space of these 2-component homogeneous coordinates considered up to an overall rescaling? How do we see this really is the sphere? So this is covered by 2 patches or 2 open sets, right? One of them, let me call it U0. This is the set where Z0 is not equal to 0. And U1 is where Z1 is not equal to 0. So the picture you should have in your mind here is, here's my sphere, there's my North Pole. There's my South Pole, and these open sets are covering kind of everything but the South Pole and everything but the North Pole, right? Okay, and so then suppose I'm on the patch U0, that means that Z0 is not equal to 0, so I can just factor it out, right? And then that's equivalent to the thing I started with because I'm just multiplying by a non-vanishing complex number. So I can take Z alpha to be Z0 times, say, 1 Z1 over Z0. And that I have to consider as being the same as 1 Z1 over Z0. And then I can call, so now there's only one coordinate in the game. Let me just call that Z. Right? So Z is now just a complex number. And now you can consider this to be a complex stereographic coordinate on the sphere in the usual way. Please.
In this construction, do we have some additional obviously not metric, I think. But maybe you can comment.
So you have the complex structure on the sphere. So this is enough to give you a metric in 2D or a conformal class of metrics. Yeah. But no, I've not specified a metric on the sphere yet. In one of the lectures, I can't remember which topic it's going to be on. We'll talk about this. But yeah, you're spot on. So just to conclude this now, we can write z as in the usual way as a complex stereographic coordinate. So e to the I phi cotangent theta over 2, and then we're back to our usual angular coordinates on the sphere. But of course, this thing blows up somewhere, and that's precisely the pole that wasn't in the open set U0. So to get that bit, we have to go to the patch U1, do the same thing, where now we pull out Z1, because that's the thing. So what I'm going to do, warning, I'm going to repeatedly abuse notation by interchanging the pair z alpha, z bar alpha dot of homogeneous coordinates on CP1 with the point z bar thought of as a point on the affine plane, right? So whenever I write something like z bar, you should understand that this is not a point on C, this is a point on CP1. And I've gone to some coordinate patch to lose these indices, right? But the point is, if the expression I've written makes sense, I should always be able to rewrite it in terms of these homogeneous coordinates. If I write something and you get confused about what's going on, just stop me and I'll try to clean up the mess. But does that sort of make sense? Okay. Okay, so the upshot of all of this is that our basis of our complete basis of normalizable momentum eigenstates, phi, which we wrote as e to the minus or plus I p dot x, this is the same as considering exponentials of the form, well, okay? So nothing magical has happened here. You might say, in fact, I've made your lives worse because p dot x looked pretty simple, and now I have this gnarly SL2 spinner expression. I'm going to abbreviate this from time to time to make all of our lives easier. Now let me write the abbreviation first, and then I'll explain what it means. Okay, so I'm going to abbreviate this product between this SL2 invariant product between x alpha alpha dot. So remember, this is my XA, my coordinates on Minkowski space. Contract them with my 4 Pauli matrices to get a 2x2 metric. And then I contract the rows of that metric with Z alpha and the columns with Z bar alpha dot. And I abbreviate it with this funny angle bracket, line, X line, square bracket notation. So what's going on there? So there's going to be some convenient notation which we're going to make use of throughout the lectures, which is the following. If I have a 2-spinner A alpha and another 2-spinner B alpha, so I can consider their SL2 invariant contraction, and this is just going to be epsilon alpha beta A beta B alpha, and I'm going to denote this by an angle bracket, AB, okay? These angle brackets are antisymmetric, right? Because the SL2 invariant tensor I used to define them is antisymmetric, right? And I can do the same thing with dotted spinners. And I'll call those things square brackets. Okay? So then what this means, angle bracket Z, X, Z bar, this is unambiguous now with these conventions. So this is Z alpha X alpha alpha dot Z bar alpha dot. And then to get back to here, I need to swap the order of contraction, but every time I raise and lower, I interchange one up for one down spinner index, I have to pick up a sign, because that's like swapping the order of the indices on a Levi-Civitas symbol. So that's equal to minus X alpha alpha dot Z alpha Z bar alpha dot. And that's why minus plus turned into plus minus here. Okay? So again, nothing sophisticated, in some sense, just a bunch of algebra. Okay, so I've given you this sermon for massless scalars, but in fact, you can use this two-spinner parameterization for any free massless fields in 4 dimensions. So what about, say, gravitons? Good, okay. Yeah, so this is a good question. You don't have to. Somehow this is some habit I got into. You could lose the bar, you mean these vertical bars here? Yeah, it's just, okay, so we all know what X is, but at some point there could be some other vector that we wanted to put here. It's just to make sure we keep track of where the dotted indices stop and the undotted indices stop and the dotted ones start. Nothing more sophisticated than this, yeah. Other questions? Okay, cool. Good. So, yeah, so similar parameterizations. For all massless free fields in 4D, and the example that we'll keep coming back to is a graviton. So this is a spin 2 massless free field, which I assume to satisfy the linearized Einstein equations around Minkowski space. So, so usually we'd write this as some perturbation of the metric HAB, which would just be some polarization tensor epsilon AB e to the minus plus I p dot x for a momentum eigenstate in a momentum eigenstate basis. And we want this epsilon is going to obey some conditions which are like gauge conditions, right? Well, some of them are gauge conditions. So in light front Lorentz gauge. So what, I mean, I wrote those words, but I'm just going to write some equations which tell you what they mean. So we're going to assume that epsilon AB is symmetric. We're going to assume that it's trace-free. And we assume that there's some fixed light front, so light vector n, which I use to define a light front gauge. And then we're also going to assume that it's transverse. So epsilon AB contracted with the momentum is 0. So this is a complete gauge fixing of a graviton in 4 dimensions. So when you eliminate all the gauge degrees of freedom, there are 2 on-shell degrees of freedom remaining for a graviton in 4D. This is a fun exercise. You can go through the counting in any number of dimensions. Convince yourself how many on-shell degrees of freedom a graviton has. You could do it for a photon as well. But in 4D, after you soak up all the gauge degrees of freedom, there's only 2. And these can be organized into what's called a helicity basis. And for us, we're going to call these helicities plus and minus. So epsilon plus AB. I'm going to write this in the 2-spinner formalism, which means that for each of these indices, A and B gets turned into a pair of SL2 spinner indices, right? So this is, think of this as some epsilon plus alpha, alpha dot, beta, beta dot. And we'll always write these things as the following way. So here, this 2-spinner I've called iota. This is just some fixed constant 2-spinner. And Z and Z bar label the point on the celestial sphere corresponding to the graviton's momentum, P. Okay. And similarly, the negative helicity polarization, this thing is going to be equal to Z alpha, Z beta, iota bar, alpha dot, iota bar, beta dot over iota bar, Z bar squared. Now, it's easy now to check that these things obey all the gauge conditions we wrote down before. So why? So first of all, they're clearly symmetric under exchange of these pairs of spinner indices. They're also trace-free, because if I contract with the Minkowski metric here, that's like contracting alpha with beta and alpha dot with beta dot. But remember, those are anti-symmetric contractions. So contracting iota with itself gives 0. Contracting Z bar with itself gives 0. Same thing's happening down here. Right? So we're trace-free, we're symmetric. Now we're supposed to be annihilated by some null vector. Well, the null vector here is just iota alpha, iota bar alpha dot. Remember, every null vector I can write is a pair of 2 complement spinners. So I take my favorite light front gauge fixing vector. It's null, which means there's an iota and an iota bar associated to it, up to little group scaling. Doesn't matter what that scaling is, because these polarizations are scale invariant with respect to iota. Right? I have 2 iotas upstairs, 2 downstairs. 2 iota bars upstairs, 2 iota bars downstairs. So it doesn't matter which iota and iota bar up to scale I choose. Okay, so we're in light front gauge. And then if I come through and contract this with the momentum, for the positive helicity guy, I'm going to get a Z bar contracted with a Z bar, that's 0. For the negative helicity guy, I'm going to get a Z contracted with a Z, that's 0. Okay? So what I haven't explained to you is why calling this thing a helicity basis is a good choice of terminology. For now, you're just going to have to take my word for it, that these really are what you would call positive and negative helicity polarizations of the graviton in 4 dimensions. Okay, so so far I haven't said anything about celestial holography, so let's make an effort to do what we're actually supposed to do, but it will build on this discussion.
So for this graviton, we have any scale appearing somewhere? Omega type.
Okay, great question. So the omega is up in the exponent of e to the I p dot x. It's not appearing in the polarization. And you might worry that that means the polarization isn't going to be invariant under the projective rescalings of Z and Z bar. But it's actually not supposed to be invariant, because the graviton carries little group weight. It has a, and that's precisely the scale that's appearing in these choices of polarizations. So the polarization tensors are not scale invariant, but they're not supposed to be, because the graviton carries little group weight, because it's a spinning field. Great question. Other questions? Going once, going twice, okay. Okay, so now for something completely different, we're going to talk about something called the conformal primary basis. So observe that the Lorenz group SO1, comma 3, this is identical to the Möbius group, or the 2D conformal group, SL2C, identical, locally identical, identical at the level of algebras. Okay, so this observation isn't rocket science, and for decades and decades, people have been thinking about some way to exploit this fact, that somehow if you're computing scattering amplitudes or some observables which are Lorentz invariant, there should be some imprint of the fact that these things are also, in some sense, 2D conformally invariant or covariant. Sorry, say that again?
Doing identical as the homomorphism something? Homomorphism.
Oh, the homomorphism. Yeah, so this is a local isomorphism at the level of groups. So the groups are not identical. One's a double cover of the other, I guess. But at the level of algebras, they're identical. The algebras are isomorphic, yes. Mm-hmm. So, okay. I'm still lying to you. Well, no, that's true. But the way you could forget about all your worries is if you complexified this. So SO4C is isomorphic to SL2C. Let's not worry about reality conditions for now. This is like what I wake up and I say every day. Let's not worry about reality conditions today, Tim. But yeah, sorry. Have I addressed your question? I mean, isomorphic is Lie algebras. Yeah. Okay, yeah, sorry, thank you. Okay, so long have people tried to make this completely, Wikipedia level observation into something with teeth, and in some sense, well, okay, now I say things that not everyone might agree with, but for my money, this whole field of celestial holography has emerged from some kind of trying to turn this statement into something precise that has teeth just at the level of kinematics. So let's let phi plus minus, sorry, get my conventions right, minus plus x, this is e to the minus plus I. This is our incoming or outgoing scalar momentum eigenstates. And now let's do something kind of funny with these. Let's take a Mellin transform of these wave functions with respect to their frequency. So remember, we just talked about you can parameterize this null momentum p with a choice of scale or frequency omega and a point on the celestial sphere. So I can think of these things as functions of x that depend on omega, z, and z bar. So here I'm committing my notational sin that I warned you I would commit time and time again. This z and z bar labels a point on the celestial sphere. Omega labels the frequency, and we're gonna take this integral over the positive real line with respect to omega, and there's some weight delta in the game here, right? So 0 to infinity, the omega delta minus 1, exp plus or minus I omega z x z bar. Now, okay, so I said this thing is called, it has a name, it's an integral transform called the Mellin transform. If you've never heard of a Mellin transform before, don't worry, it's just this integral, okay? Yes?
Lambda, which values could take?
Delta.
Sorry.
We'll talk about this in just a second. For now, delta can be any complex number, let's say. Now, you might get worried, right? You might say, well, if delta is any complex number, this integral, does it converge, right? And in fact, if you just throw this to Mathematica, not that that's a good thing to do with your lives, but if you did, Mathematica would say, I can't do this. This is some like thing that's oscillating around what's going on. But in fact, we cheated already back here in momentum space. So I gave you this sermon about LSZ. It's like you're solving some equations of motion asymptotically, free equations of motion. And if we have a scattering problem, there's this additional implicit assumption that there are asymptotically flat regions of our spacetime. And these wave functions, this basis of wave functions we're using, is also supposed to be a set of asymptotically flat solutions. Well, e to the I p dot x is not asymptotically flat. It's just an oscillator. Okay? So what there secretly is here, which we never write, is some I epsilon, which exponentially damps the thing at infinity. And if you're careful and you carry that through here, there's a damping factor that appears in the exponent here, which is just minus epsilon omega. Right? And now, if you give this to Mathematica, it converges every time for every value of delta, generic complex value of delta. What does it give you? Jiminy. Yeah. Yeah, very good, very good. You should find it strange. So we'll refine what delta is allowed to be in a moment. But yeah, you should find it strange. Yeah. Right. So what is this Mellin integral? Jiminy cricket. There's a lot of chalk. Sorry. Is it unique? Is it unique? So I haven't gave you some weird words here, and then I just threw this integral up on the board. I will argue that it is a unique transformation which satisfies some properties that I'll be very explicit about in a moment. So far, this is just something you can do. You can take many integrals of many different functions. Oh, geez, Louise. Yeah, and sorry. Who asked the question? Ah, sorry. All right. Yeah. So. God, I'm sorry. Yeah. So far, I haven't given you any rules for why you should write this thing down. It's an integral you can write down. As we'll see, it converges to something more or less sensible. But then we'll kind of a posteriori understand why this was the unique thing we could write down that did something nice. And I'll explain what I mean by something nice in a minute. Sorry about that. Okay, so this converges to the following. I mean, this is something you can also just look up. So there's a Wikipedia article on Mellin transforms. It's a huge table of these things. You'll find this answer in the table. So it converges to this object, and you see that you can just take this regulator epsilon away. So you kind of put the regulator in to ensure that this integral was going to be exponentially damped in the large omega region, but in fact, the thing was convergent anyway. So with these regulators, it's the sort of thing where like I'll be careful about them when they deserve to be thought about carefully, and I'll kind of forget about them otherwise. So this is something we're going to call phi incoming, outgoing subdelta of x, z, and z bar. So this object is just notation for the Mellin transform of our momentum eigenstate. We're going to call this the conformal primary wave function, and I'll now try to justify that, that terminology. Okay, but at this level, like I said, I've just done something more or less random. I've taken momentum eigenstate, I've integrated out the energy scale and replaced it with this complex number delta. And you're absolutely right to be a little worried about that because that energy scale was something that had some physical value for starters. Where did that physical value come from? From a mathematical perspective, it came from the demand that the momentum eigenstates formed a complete normalizable basis of solutions to the wave equation, which were asymptotically flat with an appropriate I epsilon prescription with respect to the Klein-Gordon inner product. Okay? So we should expect that we'll get some constraints on what this delta is allowed to be by demanding something similar for these conformal primary wave functions.
Excuse me, I am going to comment about that.
That's exactly what I'm going to do.
Both invariant.
Yes, don't worry. Yeah, yeah, indeed, indeed. So
Wait, so now Z and Z bar still live in CP1, right? We no longer have the scales of character.
yeah, absolutely, absolutely. And again, I shouldn't be surprised about this because the thing that allowed me to have that projective invariance was precisely omega, and I've integrated it out now. Yeah, very good.
We can start some equivalent stuff. It's like, I mean, we take project this invariant, scale invariance, and in this integral, it is in this definition.
Yeah, very good. So this measure does not respect that invariance. Yeah.
Defined up to R delta.
Yeah. So very good. So if I do these projective rescalings, I get some power of R to the delta, R bar to the delta, and that's precisely the Jacobian associated with a conformal transformation, alluding to Kim's point from before. Yeah, very good. So these wave functions obey the following three important properties. So one, they satisfy the wave equation with asymptotically flat boundary conditions. Two, good, okay, so here I'm being really, really simple, or I'm gonna be very naive. I'm gonna just say for very large values of some components of X, this thing needs to go to 0. And I'm gonna be deliberately vague about that. Yeah, exactly. But I'm not even gonna use the words null infinity. I'm just gonna say at very large X and be deliberately sloppy about that. Yeah, so they form a complete normalizable basis of solutions for delta restricted to be on the principal continuous series of SL2. So that means delta has to be equal to 1 plus I times a real number. This removes the thing you were worried about before because now there's one real line's worth of degrees of freedom.
How do you prove that?
I will prove it for you in a moment. And 3, under the action of the Lorentz group, on, if you like, on X, so on Minkowski space, these wave functions transform like a conformal primary of weight delta on the 2 sphere. So if you like, in Z and Z bar. Okay. So now let's prove these statements.
Conformal, you mean global conformal?
Yes. Yeah. Box phi equals 0 in X. So X, remember, X is still positioned in Minkowski space, just like it was in e to the I p dot x. So these things are still meant to be linear, free scalar fields on Minkowski space. All we've done is screw up the way we parameterize them. Okay? Yeah, we haven't touched X. Well, I mean, okay, it's wound up as a rational function in X now rather than as an exponential, but we haven't done any integral transform in X or anything. Okay, so property 1, this is an exercise. Just hit this thing with the wave operator, see what you get. You can see why it's going to work, right? Because if I take 2 x derivatives of that thing, I'm going to get some z's and z bars. And if I contract those x derivatives, I'm going to get z's and z bars contracted together, but that's going to give me 0, right? So it's straightforward to show that this thing obeys the wave equation. The fact that it dies off asymptotically places some restriction on delta, right? So for that, we have to have the delta, which I said was complex. So that means I can write it in terms of a real part, which I'll call C, and some imaginary part, which I'll call nu, for C greater than 0, right? So that's just saying that the real part of this thing goes like 1 over some positive power of x as x gets very large, so it's going to die off. So that's the totally unsophisticated sense in which I mean that these things are asymptotically flat solutions. It doesn't constrain the imaginary part. That's just something that's bouncing around, doing its thing. Okay, so perhaps the most non-trivial part of this is 2. So for property 2, we're trying to establish that these things form a complete normalizable basis of solutions. So to do this, we note that any momentum eigenstate, plus or minus I omega z x z bar minus epsilon omega, this can be written as a superposition of these conformal primary guys in the following way. So the theorem is that any positive frequency momentum eigenstate can be written as a superposition of these conformal primary wave functions with conformal dimensions of this form, okay? And we know that the momentum eigenstates are a complete basis of solutions to the wave equation, so that means these guys are a complete basis of solutions to the wave equation because I'm just changing basis. I can write any basis element here in terms of basis elements here, okay? It doesn't establish that they're normalizable yet. Yeah, so the assumption here is that the plane wave that I started with was positive frequency. Yeah.
That was from the very beginning.
What's that?
That was from the very beginning.
Yes, yes, absolutely, yeah. Mm-hmm. Okay, so now I'll remind you of the Klein-Gordon inner product for scalars. This is just, if I have two scalars, phi 1 and phi 2, this inner product is just minus I integral over some constant time slice, just like Simone was talking about. Phi 1 dt phi 2 bar minus phi 2 bar dt phi 1. This just comes from the boundary bit of the action you get when you integrate by parts. And this is a constant time hypersurface. So let's let delta 1 be c plus I nu 2, delta 2 be c plus I, nu 1, nu 2, and let's consider the inner product between two of these guys with delta 1, delta 2. Okay? So what is this equal to? Well, you get a bunch of integrals. So you have your 3 spatial integrals over your constant time slice, and you have 2 melon integrals, omega 1 to the c1 plus I nu 1 minus 1. Integral omega 2, 0 to infinity. Now we have c2 minus I nu 2 minus 1. We have an omega 1 plus omega 2. That's just coming from the time derivative. And then we have a big exponent. There's the frequency part, and then there's some spatial part. And I'm going to be super vague about how to write this. But this can be made precise. Okay. So now we just turn the crank and start doing as many of these integrals as we can. So the spatial d3x integral, very roughly speaking, this is going to give something like minus plus 2 pi cubed. Then you're going to get a 3D delta function with this object in parentheses. Now because it's spatial, there's some time-like 4 vector that has to be contracted into everything, but I'm not going to waste time explaining what that actually means. And you can, okay, so this t is some time-like 4 vector to make sure that these things actually live in a spatial slice, because if I covered up t, then each of these terms is just a null 4 vector, so I have to project this onto the spatial slice. And then what I can do is so the free indices here are alpha, beta, symmetrized. So that's a 2x2 symmetric matrix that has 3 degrees of freedom. Right? So that's the 3-dimensionality of this delta function. And now you can just project this onto what we would call a spinor dyad. That's just a basis, iota alpha, omicron alpha of undotted spinors. And you can normalize this basis such that angle bracket iota omicron is equal to 1. And when you do that, what you get is minus plus 2 pi cubed, a delta function in omega 1 minus omega 2, and then a 2-dimensional delta function on the sphere, which is roughly like omega 1 z1 minus omega 2 z2, and the complex conjugate one. Okay? So I'll just write that as delta 2, but what I mean is this thing and the one with z bars. And here, I really do mean z thought of as an affine coordinate, because picking this spinor dyad and normalizing it in this way like picks a hemisphere of CP1 for you. So this is these sets of delta functions are equivalent to this 3-dimensional one on that patch. Okay, so now, if we go back to our Klein-Gordon inner product, now we can do one of the Mellin integrals against this delta function, which is going to set omega 1 equal to omega 2. Right? So what we're left with here, this is going to be minus plus 2 pi cubed. Let's do the one, say we did the omega 2 integral against that delta function. So what I'm left with is omega 1 2c minus 2 plus I nu 1 minus nu 2. Sorry, that's minus 3 delta squared z1 minus z2. Okay, so when I did the omega 2 integral, I set omega 2 equal to omega 1 because of this delta function. That meant I set omega 2 equal to omega 1 here, and I could pull out a Jacobian. That's what's cranked up the powers of stuff going on here. So this delta function doesn't depend on omega anymore, so it can come out. I just said it could come out, so I should write it. Okay, so we're left with one Mellin integral left to do with a very precise exponent here. This integral is exponentially divergent for almost every choice of C and nu 1 and nu 2 thought of as complex numbers. Okay, you can easily see that. Let's see. Let's let omega equal log of t. Change variables, and this will turn into an exponential integral that's going to diverge either for the large omega regime or the small omega regime, depending on the signs of various things here. But this thing converges. This integral is precisely equal to a delta function in nu 1 minus nu 2 if and only if C is equal to 1 and nu 1 and nu 2 are real. In that case, then what you're going to get is, if you do that change of variables to make it an exponential integral, you're going to get precisely integral, say, over t, e to the I t nu minus, e to the I t omega 1 nu minus nu 1 minus nu 2. So this fixes what this value of c had to be. And then when you do that, we now have that the inner product between phi 1 and phi 2 is precisely what you would expect it to be for a normalizable thing. So you have some powers of 2 pi, then you have a delta function setting the conformal dimensions to be equal to each other, and another set of delta functions setting the points on the celestial sphere to be equal to each other. So that's where that condition came from. Okay? So this, I want to emphasize, this condition did not come from it being a complete basis. It came from it being a normalizable basis. Okay? And then the third point, that these things transform like conformal primaries under the action of the Lorenz group, that's also obvious. The thing went like 1 over angle z, x, z bar to the delta. Right? So if I do a conformal transformation, if I do a Lorenz transformation in x, and a conformal transformation in z bar, that's going to kick out precisely the right power of the determinant of the Jacobian of the conformal transformation for it to be a conformal primary. Okay, so, yep.
But I thought that the Lorentz transformation is a boost transformation in a given direction.
Yeah.
How can I see it? From
So if I think of the denominator, I had this, sorry, why am I using my hands when I have the denominator went like this. For the delta, you could think of this as kind of q x to the delta, where this q labels a direction. So it's kind of clear from this that it's going to do the business, right? Okay, so returning to the judicious question, yes?
For it to be normalizable, it implies that the delta has to be 1 plus IF, right?
Mm-hmm.
On the other side, for it to be a complete basis, what does it imply?
For it to be a complete basis, you needed delta to be some positive real number plus something. It didn't need to be 1. A way you can, this is also sort of true in a momentum eigenstate basis. To be a complete basis of solutions, you don't need the frequency to be positive. It can be any number, right? So it's only the normalizability that restricts it to being a positive real number. Yeah. So, but to come back to the judicious question we were asked earlier about why the heck did we write down this integral transform, this is the answer. This is the unique integral transform that has these 3 properties for massless wave functions. Now, I'm only ever going to talk about massless stuff in these lectures, but just as a point of education for everyone, you can also define wave functions that satisfy these 3 properties for massive free fields, but the integral transform is not a Mellin transform anymore. It's something a little more gnarly, okay? And if you look in one or two of the references I gave you at the beginning, they'll explain what this integral transform is, but I won't. Okay. So we worked through this for scalar wave functions in some detail, but it also works for any massless spinning free fields also. So like the gravitons we wrote down before, with their helicity, in their helicity basis. So there's a similar story for massless spinning fields. So for instance, if we use our example of the gravitons that we wrote down before, you could take these things we wrote down a helicity basis of their polarization tensors, either plus or minus. These things only depended on z and z bar. They didn't depend on omega, so they can cruise right outside of any Mellin integral, and then we could just take the Mellin transform of e to the plus or minus I omega z x z bar minus epsilon omega and get some epsilon plus minus AB plus I delta gamma delta zx. It's just the obvious thing. It's basically just the scalar conformal primary wave function dressed by a polarization tensor. Okay. And you can show that these things still solve the linearized Einstein equation with the right asymptotically flat boundary conditions with the same constraints on this conformal dimension. And you can show that they form a complete and normalizable set of such solutions. However, this dude does not actually transform like a spin 2 formal primary. But it's gauge equivalent to something that does. So it doesn't actually transform like a spin 2 conformal primary in S2, but there's a linearized diffeomorphism you can do on Minkowski space, which takes this thing to something god-awful. So I'll write it down once, and then we'll forget that it ever happened. So there's this awful thing that I've written in parentheses here that has a free alpha and alpha dot index. Write the same thing with a free beta and beta dot index. And here, I've gone to some patch on CP1 where one of the components of Z is 1 and the other one is some affine coordinate Z. And then I pick my constant spinner iota so that it only picks out the 1. Okay, so this, what I've written, is not actually a global expression on S2. You could make it global, but then I'd have to decorate this expression with lots of factors of this, and I don't want to do it. Okay, so what one typically does is works with this expression, and you trust that you're only ever going to be using these wave functions to compute something gauge invariant, like a scattering amplitude, which means you should get the same answer if you use the thing that really transformed like an honest spin 2 conformal primary, okay? But the upshot is just like there's a way to do this for any spin, massless free field. So now, let me say something kind of slightly hand-wavy, but nonetheless important. So now consider any scattering amplitude in a massless QFT. This is going to be some function of the quantum numbers of the external states that we're scattering. Usually we do this in a momentum eigenstate basis, so that means the thing is going to be a function of the frequencies and the positions on the celestial sphere of all of the external states, incoming and outgoing, right? Okay. It may also depend on other quantum numbers, which I'm suppressing, like charges, colors, helicities, whatever. Okay. Then we can define the following object, which depends on conformal dimensions delta and points on the celestial sphere, to just be the Mellin transform in each of the external frequencies of the momentum space amplitude. Okay? And then, by definition, because of the properties that our conformal primary wave functions satisfy, this m twiddle n will transform like a conformal correlator on the celestial sphere. Okay? So this is really, at least for me, this is like the statement that motivates celestial holography. There's some set of states that we can use to parameterize a massless scattering process, or I didn't show you why, in fact, any scattering process, massive or massless, such that the scattering amplitudes look like conformal correlators on the two-sphere. This is a completely kinematical statement. No dynamics in this statement at all, right? We just found a way to solve the wave equation with a complete normalizable basis of states that had this property, right? The amplitude, the momentum space amplitude is a multilinear function in the external states, so I can just Mellin transform all the external states and get this thing that is often called a celestial amplitude. Okay? So these celestial amplitudes look like they came from correlation functions in some 2D CFT that lived on the celestials. So the pipe dream of celestial holography is that this kinematical statement is actually the harbinger of a dynamical statement. That there's actually an actual CFT living on the celestial sphere whose correlation functions produce the S matrix of some theory. This has not been realized, okay? And I think it's, maybe at the very end, I'll give you some sermon about special examples where it's sort of been realized. But these are not examples you'll meet in the real world. Even if you're an ADS CFT person, you wouldn't consider them real world examples. So we'll also see that if there is such a CFT, it has to have some weird properties. You're not going to find it in the big yellow book. So that's bad news, because we all go to sleep with that book under our pillows. But yeah, okay, I think it's coffee time, so I'll stop here, and then whatever, we're back in half an hour for more madness. Okay.